examples. First of all, here's my matrix A. It is going to be -2, 1, -1, -4. -2, 1, -1, -4. And we are working again with the differential equation x prime equals ax. And I want to find a general solution. So same process we've been working with all the way through this chapter. A equals -2, 1, -1, -4. I'm looking with the differential system of equations, vector x prime equals a times vector x, and I want to find a general solution. Two things I have to check: constant coefficients and homogeneous. Give me a thumbs up. Constant coefficients and homogeneous, we're good on both of those. Constant coefficients and homogeneous. Good, yes, thumbs up, cool. All right, so first thing I need to do is find my eigenvalues. You can do this as well as I can. I need determinant of lambda I minus a to equal 0. So 0 is going to need to equal the determinant of lambda plus 2, -1, +1, lambda plus 4. That's my determinant that I'm looking for. We'll keep going. So this is going to be lambda plus 2 times lambda plus 4 minus -1. We're good there. Lambda plus 2, lambda plus 4 minus -1. And if you do the simplification, I get lambda equals -3 and -3. So those are my eigenvalues. I've got a repeated eigenvalue of -3 in this case. I'm not sure yet if it's defective. I need to see what happens. I need to check, so we need to plug in and decide if this is defective or not. I don't know. So I am going to get -1, -1, 1, 1. I am plugging lambda equals -3 back into my lambda I minus a matrix. Plugging in -3 into my matrix up here. All right, so we get -1, -1, 1, 1. I need to zero out the 1 in the bottom left. So we can do row 1 plus row 2, get sent to row 2, and that gives me -1, -1, 0, 0. All good? This is a review. I haven't done anything new yet. So far, so good? Okay, let's do leading variables and free variables. So again, we'll call these V1 and V2. So leading variable, that -1 is a leading non-zero coefficient. It goes with V1. And then there are no leading coefficients in the second row. Everything's 0. So therefore, my free variable is going to be V2. Give me a thumbs up or thumbs down for defective. Yes or no for defective. Look at algebraic multiplicity. Look at number of free variables. Yes or no for defective. What do we have? Yes or no? Give me thumbs up or thumbs down. I am getting thumbs up. Yes, yes, defective. So yes, this is defective. All right, because this is defective, I need to find V1 and V2. So here's what I need, copying from the previous slide. Lambda I minus a quantity squared times V2 equals 0. I need that. I need lambda I minus a times V2 to equal V1, copying from the previous slide. And I need V1 to not be the 0 vector and V2 to not be the 0 vector. Those are the things that I need in order to hopefully find my two linearly independent solutions. I just copied that verbatim from the previous slide, totally copying from the previous slide. All right, so let's go ahead and look at, and you should figure out matrix multiplications on your calculator, by the way, because that's going to make life a whole lot easier. So let's look at lambda I minus a quantity squared. I'll do this one by hand once, and then we're not going to do them by hand after this. So lambda I minus a squared is -1, -1, 0, 0. And then when you square, you multiply something by itself, right? So -1, -1, 0, 0. All good? Seeing where that's coming from? Nope. Sorry, that's not right. Let's try the matrix before I did my elementary row operations. So the matrix that I just put down was the matrix after my elementary row operations. I want the one before my elementary row operations. Instead of zeros in the second row, I have ones in the second row. Sorry about that. Make sure you're using the right matrix to do lambda I minus a squared. All right, if you multiply matrices out, you can do this. If you do this by hand, you are going to get the zero matrix. Multiply matrices out, you're going to get the zero matrix. Okay. I don't know. Let's call this A and B up here just to have some letters. So basically what I've got is 0A plus 0B equals 0, right? This first equation needs to be equal to 0 from my first requirement over here. This first equation needs to be equal to 0. So I need to have 0A plus 0B equals 0. I can pick anything I want. I don't care. So let's choose A equals 1 and B equals 0. It doesn't matter if you make a different choice for me. That's totally fine. You absolutely can. Doesn't make a difference. Different choice is fine. I am in my first equation over here. Yes, I'm in my first equation. So therefore, what I've just found is V2. So my vector V2 is the vector 1, 0. That's going to be my vector V2. Do we understand why that's my vector V2? I'm working with the first equation over there. That's my vector V2. Okay. I also need V1. So here's the other thing that I need. I need lambda I minus a times V2 to equal V1. That's nice. I've got the whole left-hand side. Everything on the left-hand side is something that I know, so I can plug in to get V1. Here's my V1. It's going to be -1, -1, 1, 1 times 1, 0, right? That whole left-hand side, I know what that whole left-hand side is. If you multiply out, you are going to get, sorry, I usually do this with my fingers, -1, +1. Okay, -1, +1. All right, have I met my third requirement? Did I choose wisely? Have I met my third requirement in the list of stuff that I'm supposed to have for V1 and V2? Thumbs up, thumbs down. Have I met my third requirement? Did I choose wisely? Yes, good, yes, okay. And so here then are my linearly independent solutions. So remember x1 is V1 e to the lambda t. So in this case, that's going to be e to the -3t times -1, 1, right? That's my x1. E to the -3t times -1, 1. And my vector x2 is going to be V1t plus V2 e to the lambda t. Again, this is the part that I told you comes out of nowhere. And if I had you in the classroom, I would show you where it came from. And so this then is going to be -1, 1 times t plus 1, 0. And all of that is e multiplied by e to the -3t. So -1, 1 t plus 1, 0 e to the -3t. If you wanted, you could double check that those are linearly independent. And if you wanted, you could verify that both of those are solutions to our original system of equations. Remember, our original system of equations looks like this up on the top of the screen. X prime equals a times x. So if you wanted, you could check that x1 and x2 actually satisfy that original system of equations. You could double check. You'd have to take a derivative, start on one side, etc. So my general solution, final answer, just enough space on this slide to do it. General solution is vector x equals c1 vector x1 plus c2 vector x2. Box that. Sorry, this slide got really messy because I was trying to keep everything on the same slide. I don't know whether that's good or bad. Messiness, but everything being together. All right, I think from what I can see of you that you are caught up. So I'm going to stop sharing my screen and ask if we have questions at this point in time. Anything for questions at this point in time? Otherwise, we're going to do 3 by 3 one. Seth, yes.
Could you have an eigenvalue being defective and another one being not defective?
You are leading into my very next example. Thank you for the question. Yes, absolutely. Not in the 2 by 2 case, because if you have eigenvalues of multiplicity 1, they are never going to be defective, and so you'll get 2 distinct ones. But in a 3 by 3 case, yes, what you just described can happen, and I'm pretty sure that's my next example. Yes, good question. Other questions? Feeling okay about the process? Kind of sort of making sense? Doing all right? Okay, all right. Let's do a 3 by 3 one. And I am going to, does somebody have their calculator, and does somebody going to be able to square a matrix for me? I don't have mine and my notes are slightly different, so I'm gonna task somebody with being able to square a matrix for me, all right, when we get there. Okay,